Nobody will sit till you sit.
Actually, we sat a long time ago.
Good morning. My name is John Hennessy, and I have the great privilege and honor to be Stanford's 10th president and to be here today celebrating our 30th Nobel Prize. Of course, this is our second Nobel Prize this week. I have to observe that we were once before on this occasion when Roger Kornberg and Andy Fire won the Nobel Prize together. I've known Michael for a long time. He is one of the most creative people. He was interdisciplinary before it was fancy to be interdisciplinary, and he was interdisciplinary because the work and the vision that he had required that he master disciplines, from physics to chemistry to biology to computer science. He was a computer hacker when that was a good thing to be. Now he described himself as a computer geek. We met many years ago. I was interested in building fast computers. He was interested in using them. And Michael became a leader in the field that he helped start, computational structural biology. I think his dedication to multidisciplinary research, this event today on a day when we celebrate the 10th anniversary of our interdisciplinary initiative, BioX, something that Michael was highly influential and a great advocate for, really celebrates what we can do together. I think great science and great people dedicated to their science is what the Nobel Prize is all about, and Michael is a great inspiration in that regard. Let me turn it over to my colleague, Jennifer Whittam, Chairwoman of Computer Science.
Thank you, John. As John mentioned, Michael is an amazing computer hacker, actually. We've had a long-time friendship with him in the computer science department. He's not just a hacker, actually. His knowledge of computer science is very deep. And he was an extremely early pioneer in using computing to make scientific discoveries. And that's becoming more and more popular, but he foresaw that by decades, I would say. And I'm going to trust that his biology and chemistry knowledge are deep as well, but I know he's a very deep computer scientist. So we're really excited in the computing side of things to see world's biggest scientific prize go to someone who's used computing power to make discoveries. And we hope there's more of that to come. So congratulations, Michael.
Good morning. I'm Lloyd Minor, Dean of the Stanford School of Medicine, and I have the privilege of welcoming you here today with the President, with the Chair of Computer Science, and also in acknowledging some very special guests we have with us here today. Dr. Roger Kornberg, recipient of the 2006 Nobel Prize in Chemistry, is here. Dr. Kornberg is a professor also in structural biology here at Stanford. And also Dr. Brian Kabilka, recipient of the 2012 Nobel Prize in Chemistry and a professor in our Department of Molecular and Cellular Physiology at Stanford. Also with us today is Dean Ann Arvin, the Vice Provost for Research, and Amir Dan Rubin, the President of Stanford Hospitals and Clinics. Now, as John indicated, it's been a sleepless week for us here at Stanford Medicine, having two Nobel announcements in just 2 days. And I'm honored and delighted to share our congratulations with Professor Levitt for winning the Nobel Prize in Chemistry. It's a tremendous achievement for him, for science, and for Stanford. I'm so pleased that Professor Levitt's deep commitment and perseverance, collaborative spirit, and vision have been recognized with this prestigious award. It honors his unrelenting focus and his integrity. Michael's work breaks boundaries. He applies the tools of physics, chemistry, and computation and applied mathematics to unravel molecular and cellular structural basis of biology's most fundamental processes. His remarkable research deepens our understanding of the mechanisms behind how macromolecules function and interact, and computer models that he has developed mirror those real-life events and occasions and activities for which his models have contributed such a great understanding. His contributions have revolutionized our understanding of the relationship between the structure and function of macromolecules, and there are virtually no areas of biological or biomedical sciences that have been unaffected by his work. On a very pragmatic level, His work has provided us with a better understanding of how proteins interact with pharmaceutical drugs that are used in the treatment of many diseases. Science stands at the threshold of a new frontier in the diagnosis and treatment of human disease. We're in the midst of a biomedical revolution that offers truly dazzling possibilities for improving the human condition, for treating and curing disease, and for enhancing life and health. Stanford Medicine is leading that revolution, and certainly Dr. Levitt joining the 5 other Nobel laureates in the School of Medicine illustrates this clearly. And I also want to acknowledge Professor Andy Fire, also a recipient of the 2006 Nobel Prize in Physiology or Medicine, who's here today with us. We lead that biomedical revolution by being the epicenter of innovation. Our scientists and clinicians are attracted to the most difficult problems, to the problems that require the most innovative approaches and transformative solutions. For more than 40 years, Dr. Levitt has been a pioneer, literally a founder, as John said, of the field of computational structural biology and computational biology. In an interview more than 12 years ago, he predicted that one day he, quote, would like to be able to simulate complicated biological processes, perhaps even going from the genomic sequence to a full simulation of an organism's phenotype. I have no doubt that his prediction will be realized, and because of his influence, very likely here at Stanford Medicine. It's now my great privilege and pleasure to introduce Professor Michael Levitt, recipient of the 2013 Nobel Prize in Chemistry. Michael?
Thank you very much, President Hennessy, Chair Woodham, and Dean Miner, and thank you all for being here. It's really great to see so many faces that I've known and met over the years at Stanford. This is probably the most exciting thing, just to see everybody here and sort of feel part of this amazing experience. Today started out for me at 1 a.m. when I went to sleep and then was awoken an hour and 10 minutes later. One thing I did that probably wasn't really smart, my Stanford phone number is a fictitious phone number. It's actually a Skype-in number. And the main idea is I never answer the phone, I just get messages. And then I guess for whatever reason a few days ago I made it forward to my cell phone. The trouble with that is you get no caller ID. I mean, all the calls come from Palmdale or somewhere like that, where Skype's in number is located. So this is not such a great idea. I should have turned off the forwarding really early on. Anyway, it was really exciting to get the call. I was very impressed by, the Swedes really do have an amazing way of doing this. I mean, I think they deserve incredible credit for just how they're really, really good at ceremony. And you speak to the chairman, and then you speak to somebody else, and all of this was sort of formal. And then towards the end, they had me speak to 3 or 4 friends whom I know in Sweden, and each of them made a point of saying something very personal, like, you promised to send us that review 2 years ago. You can still get the prize if you send it in. Or another friend who said, remember that night we got drunk in Italy? Another one said, you don't want to go sea kayaking in Stockholm in December. And it was just, that really sort of made me suddenly come to grips with the fact that it was actually happening, those people, because otherwise it could have been a really elaborate hoax. I don't think anyone would bother to do that for me. I should also say that you probably don't know this, but there actually are websites where people make predictions about who's going to get the Nobel Prize. And I'm happy to report I wasn't on any of them. So I guess I was a long shot. And I think, before saying a little bit about the work, I think, as has been said before, I guess by all the other speakers, there's a very clear computational aspect in this prize. And one of the problems, I suppose, with computer science is that there's no Nobel Prize for computer science. And this, I think, is very sad, but this really was a recognition of the importance of computation in biology. Now, you might have said, well, why not computational economics or something like this? But it turns out that there was a very tight connection between biology and computers very early on. And in some ways, we got onto that bandwagon. I actually started this work when I was 20. I had just finished my first degree in physics. I had played with computers a couple of times in the summer. I spent the summer of '66 at the Lawrence Berkeley lab and had a very interesting time. Maybe I inhaled sometimes. But I'm not going to commit on that. Fifth Amendment. But I did actually learn how to program then. And when I got to Israel in 1967 to work with a man who sadly is no longer alive, Shneur Lifson, he was the person who really had this vision of essentially applying a consistent approach to the energy of small molecules. He was dealing with small molecules. He didn't believe it would be possible to deal with large molecules. So I was sort of, Arieh Warshel, who also won the prize, was working with Lifson, essentially doing a PhD. And I came along as a summer, sort of in between BS and PhD, to spend a year there to do whatever I wanted. But I decided I would write programs for them. And the program actually went pretty quickly, considering that you're using punch cards and you can check 3 bugs a day or something like that. It's a different experience. So you thought a lot. And then pretty soon I realized that the same program that dealt with small molecules could deal with large molecules. Now, computers back in '67 were very slow. But more importantly, they had no memory. I mean, all your cell phones probably have, 8 gigabytes of memory or 4 gigabytes of memory. So the computers then had less than 1 megabyte. Very, very small, maybe 1/10,000th. And the reason this is important is that if people have been working on small molecules have maybe 50 atoms at the most. Small proteins have at least 1,000 atoms, so there's this big gap. We decided to try then, could we actually do something with a whole protein? And to our surprise, we actually could. It just turned out that the way the thing scaled, it wasn't such a big deal, and you could actually do this quite easily with, I think, 100K or 120K of memory. So this suddenly enabled this to happen, and I think this started to set the groundwork for computers in biology. As I think President Hennessy said, I'm sure I was a hacker because there really weren't computers available in the '60s. But I certainly like computers, and my wife would probably say that I love computers. And she's just got up. Hope she's not leaving. Actually, I'm pretty safe on that because she lived with me now for 46 years, so I guess that's pretty impressive. But we decided to apply to large molecules, and this sort of opened up the whole area. I then went and started my PhD in Cambridge, England, and I was very lucky. This is the lab where I met Roger. Actually, a few years later, I did a PhD there. Roger had done his PhD at Stanford, I think, and then on his way there. And I sort of had carte blanche. I was into computers. They had computers there. I was the only person there not doing experiments. And one of the reasons I wasn't doing experiments is that our first child was born like 9 months into our marriage, or some approximate number like that. So I had to be and we had no money, and Rena went out and worked, and I had to basically babysit at home. And telecommuting in those days, we didn't have even a phone at home. There was no terminals. We didn't have a card punch at home. But to my amazement, the structural biologists in Cambridge, who really were I would say there are like old Nobel Prize winners, the old great ones, and these nouveau riche guys like me. And these old guys like Crick and Perutz and people like this were amazing. And they basically accepted me telecommuting. I would run into the lab for 3 hours in the morning when we had a babysitter, type punch cards frantically, and go home. And they actually got used to it. It was like amazing. Why, and it was because I would come back the next day having done something. So I think as a result, I've always had a very high mean free path and not always ever been in one place. But those years were amazing. And I sort of see this prize as really relating to the years probably from 67 to 75. In that time, I was probably most of the time in Cambridge, a little bit of the time in Israel. I worked closely with Arieh Warshel probably for 4 or 5 of those years. He came back to Cambridge with me. And I think we were able in that time to sort of lay out the basis of all this, of computational biology. Now, at that time, people didn't accept it. There was a lot of resistance, which I think is good. I sometimes joke that if you submit a paper and it gets accepted, it obviously isn't interesting. You should immediately withdraw it, and you should only publish papers that don't get accepted. This sort of this is like majoring catch-22, but it doesn't have a solution. But in any case, we had these issues. Then the third person in the trio who got the Nobel Prize was Martin Karplus, and he also, although he's a professor at Harvard, he was also very influenced by the Livestream school. He actually came to Israel with his first wife to spend a year with Livestream in 1970. So, and then Warshel went back with him. So everything is tied together. But then the field progressed, and I must say, when I look through the lists of, I guess I can say this surrounded as I am by computer scientists, that computer science and computers in biology have not been, I think, sufficiently appreciated. Now, I can say that now that they have been. And I think the reason is that biology has always been and still is dominated by experiment. And great biologists are people who can choose a system, clean it, really classify it, and so on. And I think it's right. We're trying in some ways to use the computer to tie the loose ends together. And I would say that what characterizes the work that we do, so we want to simulate the large molecules that make everything work in cells. And because these molecules are large, we have to use computers. But beyond that, if you like, the science here is choosing the right representation. And by that I mean is, there's always this joke among physicists, we treat a cow as a sphere, and then we'll see what its properties are. And that's probably too simple. But if I said I wanted to treat a car as a billion electrons, you might say to me, well, gee, that's a little bit too detailed. And somewhere between the sphere and a billion electrons is the right representation. And right here was very simple. It had to be computable. If the calculations took too long, and I think we were lucky that it was possible to find a representation that was computable, but still accurate enough to start to make predictions. Things have come a long way since then. I would say that when I was in Cambridge, and I'm sure Roger will remember this, I always said you're as good as your next paper. And I think, and then I told my colleagues that, in fact, it's even worse in the USA because your salary depends on your next grant. So, what you take home to your family depends on your next grant. So that's even worse than you are your next paper. But I think that what has really excited me about my whole scientific career, and it's by no means over, is that it's remarkable that you get to do what you like. No one tells you what to do. I never feel I've ever actually worked for anybody. You end up working with smart young people who get younger every year, and they are generally polite and respectful, and it's just remarkable. I actually, before this happened, like if you'd asked me, yesterday morning what kind of week it had been last week, I would have said it's been an amazing week because we actually made progress on 3 very difficult problems, and I'm really excited about that. And although I'm sitting here, I'm really excited about the Nobel Prize. I'm probably really excited about getting some coffee and something like that, because I didn't want any coffee because I was so high on adrenaline, but it's starting to go down. But I was really excited about the work that's currently happening. And this also involved computer science. There was a particular calculation that a year ago took 2 hours to do, and now takes 10 milliseconds. And that kind of jump is suddenly you can do stuff you wouldn't have dreamed of, and you can do things in ways you would have totally rejected out of hand. So it opens up whole new areas, and it makes me feel very, very excited. I think that I have many heroes in science. Unfortunately, most of them aren't alive anymore. And I guess that's one of the problems with starting out early and being in the field. But one hero I have actually is not in science. She's an artist, the French-born American sculptress Louise Bourgeois. And we were in New York for a quarter in 2008, and she had a retrospective. She was alive. I think she died maybe a year after that, at the age of 94. And she was making huge spiders, and the whole Guggenheim was devoted to her. And we went in there, and we had an apartment in Chelsea, and we went to a gallery where she was, and it was very exciting. And then I actually read something that she'd written, and it turned out that in 1980, or 78 or something like that, or maybe 82. They'd made a huge retrospective for her at the MoMA. And she was 72 years old, and some press person said to her, now, how do you look back on your whole life's work? And she said, you think this is a retrospective. I'm just beginning. And she took the money that she'd made from that sale and bought a huge warehouse in Brooklyn, and all her most famous stuff happened afterwards. And that's kind of how I'd like to be. So I think it's, science is a passion. It's something which I was also asked, actually, I've been interviewed so many times, but I was asked, was there an eureka moment? And I don't think you ever really have a single eureka moment, because basically it's a lot of small steps, and each time you solve a step, that's great, but now you have another step. So basically, like many things, a lot of hard work and persistence, and it's really important not to give up. It's really important to be stubborn, and just do everything you do with a passion. And I think if everybody did everything with passion, the world would be a better place. So I guess that's sort of, I don't know how long you wanted me to talk for.
That's good, Michael.
Thank you. It's meant to be a minute, right?
We have time for one or two questions, and then I'd like to invite our three other Nobel laureates that are in the room up for a photo. But we have time for a couple of questions. None? Well, then we'll start with the photography. So would Professors Kornberg and Kobylka and Fire come on up for a photo? This is an only at Stanford moment.
They look like regular people, huh?
Okay, thank you all very much, and congratulations.